All right, how is everybody this morning?
Good.
Cool. Meh? Yeah. All right, well, we're here. We're going to try and enjoy our last day before Thanksgiving. So yeah, hopefully it'll be a good one. We're going to start with a review of diodes and transformers. So we'll talk about what they are and how they work. And then we'll go on to our main topic for today, which is power supplies. So we'll talk about what they are, why they're important, and how they work. We'll start with the general idea for a power supply, which is kind of the general principle that they all operate on. And then we will look at three specific types of power supplies: the half-wave power supply, the full-wave power supply, and then the full-wave bridge. And then we'll go on and do a preview for today's lab. And just a reminder, there's no class on Thursday because it's Thanksgiving. So I know. So any questions before we get going? All right, cool. So then let's get started. So let's review diodes and transformers. So we said that a diode, what is the main purpose of a diode? What does it do? Exactly, it's a one-way valve for electricity. It allows electricity to flow through in one direction, but it blocks it from flowing the opposite way. So we said that the symbol for a diode looks like this. And the diode has two separate sides. So this side is called the anode. And that's abbreviated with an A. What's the other side called? Cathode. That's right. And that's abbreviated with a K. So if we were to look at an actual diode, it would look something like this. It would have a wire, and then the body of the diode is typically a cylinder. And it's got a stripe on one end. And this stripe end corresponds with the line on the symbol. So the end with the stripe is the cathode. And we said that if we apply a positive voltage on the anode of the diode, and a negative voltage on the cathode, is that diode forward biased or reverse biased? Perfect. Yeah, it's forward biased. And does the electricity flow? Yeah, electricity flows through it. And what is the voltage across that diode, approximately? Yeah. That's okay. Yeah. Connor?
Around 0.6 to 0.7 volts.
Yeah, 0.6, 0.7 volts, something like that. And does that voltage change very much depending on how much current is flowing through the diode? No, it's pretty constant. So you could have a small amount of current, and you'd have 0.6, 0.7 volts. You could have a large amount of current. It stays about the same. That's very different from resistors, because in resistors, the voltage is proportional to the current. OK, so that's forward biased. Now, if we apply the voltage in the opposite direction, so there's a negative voltage on the anode and a positive on the cathode, then this diode becomes reverse biased. And does the electricity flow? No. So there's no current. And what is the voltage across the diode in that case?
It's equivalent to the applied voltage.
Yeah, Yeah, it's whatever voltage you apply, exactly. Okay, so that's a quick review of diodes. And we'll get to practice a little bit more with them today when we look at power supply circuits. So any questions about diodes? All right, cool. So then let's talk a little bit about transformers. No Optimus Prime jokes? Come on. All right. Yeah. We can use that rest for Thanksgiving. It'll be good. All right. So transformers. We said that a transformer is a device that changes the voltage and current of AC electricity. And it's really a pretty simple component. So it's really just a couple of coils of wire that are close to each other. So the first coil is called the primary coil, or just the primary for short. The second coil is called the secondary. And the ratio of the number of turns on the primary to the turns on the secondary, that's called the turns ratio, and that determines whether the voltage coming out is greater or lesser than the voltage going in. So if you have more turns on the secondary, you get more voltage out. Fewer turns on the secondary means less voltage coming out. Now, what about the power? Does the power change between the input and the output on a transformer? No, exactly. So for transformers, the power in equals the power out. And remember, power is voltage times current. So what that means is that on the output, if the voltage goes up, what happens to the current? It goes down, yeah, it decreases. So if the voltage increases, the current decreases, and vice versa. If the voltage decreases, then the current increases. So it's kind of like a seesaw. When one goes up, the other one goes down. So transformers are really useful because they allow us to change the voltage and the current of our electricity. And this can be helpful if we're trying to send the electricity over a long distance, like we're trying to transmit it down a power line, or it can be helpful to increase the voltage to do that. And then we can decrease the voltage easily with another transformer when it gets close to our house. Okay? So we also said that there was a special kind of transformer that had an extra wire attached right in the middle of the secondary. What was that type of transformer called? Yeah, a center tap transformer. And the thing in the middle is actually called the center tap. And the center tap split the output voltage right in half. So if we had 10 volts coming out, we'd have 5 from the top to the middle and another 5 from the middle to the bottom. So that's the center tap transformer. So any questions about that? All right. And again, we'll have a chance to practice a little bit more with transformers today when we talk about power supplies. All right. So any questions about diodes or transformers before we go on? All right.
What's your favorite transformer?
Yeah, right. Optimus Prime was always pretty good. But all right. So let's go on and let's talk about power supplies here. All right. So power supplies, we're talking specifically about DC power supplies here. And DC power supplies came about because there was this problem. The problem was that people used AC electricity, and they transmitted AC electricity because it was really nice and efficient to transmit it down a power line. So AC electricity looks like this. If we're looking at the voltage over time, AC electricity looks like this. It starts off at 0, and then the voltage goes up and up and up and gets to a high voltage. And then a moment later, it starts to come down and goes back to 0, and then it goes back down to a negative voltage, and it comes back up to 0, and so on. So people use high voltage AC electricity when it's being transmitted down a power line. But the problem was that a lot of electronic devices that we use in our house don't require high voltage AC electricity. They actually require low voltage DC electricity. So again, if that's voltage and this is time, then the devices in our house, like cell phones, computers, batteries, they require low voltage DC electricity in order to run. So what we get out of the wall is something like this, high voltage AC, but what we need is something like this, a low voltage constant source. So we need something that will change this type of electricity into this type of electricity, and that's what a DC power supply does. Yeah?
What exactly is the effect of a negative voltage?
So if we think about voltage as being like a pressure, you can imagine a positive voltage would be like a positive pressure pushing water through pipe in one direction. So a negative voltage would be like a negative pressure, which would be pressure pushing the water through the pipe in the opposite direction. So it works the same way with electricity. A positive voltage pushes electrons through a wire in one direction. A negative voltage pushes them through the same wire in the opposite direction. Yeah.
Absolute value, right? It's not actually like a true negative number, like it's always, it represents movement, right?
Yeah, it represents pressure pushing the electricity in one direction or the other. Yeah. Other questions? Yeah.
You said the one on the left is in AC, and then
Yeah.
right is DC.
Yeah. So this is high voltage AC. So that's a high voltage AC signal that comes out of the wall. So we said that this was like 120 volts RMS. So that would be about 120 volts right there. And then we want to transform that into a low voltage DC signal.
Oh, so AC/DC.
Right. There you go. All right, we're getting some jokes here. All right, people are warming up. All right, so we want to turn into a low voltage DC signal. Now, this output voltage can vary depending on your application. So if you're talking about charging a phone from a USB port, this would be 5 volts. If you're talking about a computer or a laptop, those sometimes run on 12 volts. So the exact voltage coming out can vary based on the application, but what doesn't change is that this is a DC signal. In other words, the voltage is constant. It stays the same over time. Okay, so a DC power supply will produce a DC voltage that is constant over time. So So this is the purpose of a DC power supply, to take high voltage AC and turn it into low voltage DC. So let's talk about how this actually works. So basically, what happens is that to get from here to there, we don't do it in one big jump. We do it in steps. So we kind of sneak up on it, all right? So the first step that happens inside of a DC power supply is that we take this high voltage AC signal and we turn it into a low voltage AC signal. We're trying to get it closer to this low voltage DC, so the first thing we do is we lower the voltage. So, so that would look something like this. It would still have the same frequency, but the voltage would be lower. So this would be a low voltage AC signal. And do we know of a device that can take a high voltage AC signal and turn it into a low voltage AC signal? Yeah. Transformer, exactly. So that's what the first part of a DC power supply is. It's a transformer. All right, so the transformer takes the high voltage AC signal, turns it into a low voltage AC signal. The next thing that happens inside of a DC power supply is that we take that low voltage AC signal and we turn it into a signal that's only positive. So we keep the positive part, and then we turn the negative part positive also. Now the exact waveform here can look a little bit different depending on which type of power supply we use. We'll talk about that in a minute. But this is always positive. There's no negative signal at this point anymore. So this is called a rectified signal. And the circuit that does that is called a rectifier. So the rectifier does this. And we'll talk about rectifiers in a minute also. So then once we have this rectified signal, we want to, this is also sometimes called a pulsating DC, pulsating DC. Once we have this, we want to smooth this out a little bit. So it's all positive, but it's got these big dips in it right now. So we want to smooth that out. So we want it to look more like this. So the way that we do that is we use something called a filter. So we've talked a little bit about filters in the past. We said that filters allow certain things to go through, but they block out other things. So in this case, we would use a low-pass filter. So that allows low-frequency signals to go through, and it blocks out high frequencies. Remember, we said that what was another name for the lowest type of frequency? The lowest frequency you could have, what's that?
Ground, right?
Well, yeah, so, So ground would be an example. The lowest frequency that you can have is something that doesn't change at all. It never moves. And so that's a DC signal, and that's what we want. So we use a low-pass filter to allow DC and things that are close to DC to pass through, but it blocks out high-frequency changes like these big dips. So we use a low-pass filter here. And the simplest type of a low-pass filter is really just a capacitor. So we use a capacitor there to smooth this out. And then the final step is that when we want to go from here over to here, we want to get rid of these final little wiggles. And we can use a device called a voltage regulator to do that. It's a little chip. And its only purpose is to take kind of a noisy signal like this and just smooth out the final bit. So this is called a voltage regulator. All right, so that's the general idea for how a DC power supply works. Its purpose is to take a high voltage AC signal like that and turn it into a low voltage DC signal that can be used to power our electronics. And we do that in steps. Yeah?
I'm sorry, can you repeat what the voltage regulator does?
So it's a little chip, and it takes a signal that's mostly DC but has a little bit of noise in it, and it just flattens it out the last little bit.
Thank you.
Yeah. So the way that we go from this high voltage AC signal to a low voltage DC signal is that we do it in steps. We kind of sneak up on it. So we start by lowering the voltage of the AC signal. We use a transformer for that. And then we take this low voltage AC and we rectify it so that it's all positive. Then we take this rectified signal, we feed it through a low-pass filter, which gets rid of most of those big changes. And that low-pass filter is really just a capacitor. So we get rid of most of those big changes. And then the final step is we pass it through a voltage regulator that does the final smoothing. It takes those little wiggles and gets rid of them and gives you a nice flat output that doesn't change. So that's the general idea here for power supplies. So any questions about that? All right, then let's look at a couple of specific types of power supplies and see how they really work. So the first type of power supply we'll look at is called the half-wave power supply. And we'll see why in a minute. So the first part of the half-wave power supply is a transformer. So this is going to be the first part of all of the power supplies that we look at. Remember, this takes the high voltage AC and it turns it into a low voltage AC signal. And then the next part of the half-wave supply is the rectifier. So for a half-wave power supply, the rectifier is just one diode. That's all it is. And then this would go to the load. Remember, the load is whatever we're trying to power. So this could be a phone that we're trying to charge, or a laptop we're charging up, or a computer that we're supplying power to. So this is our load here. And that's really all that that's sort of the simplest version of the half-wave supply. So let's look at what the signals would look like in this half-wave supply. So over here, this is where we have our high voltage AC, and then the transformer takes that down to a lower voltage AC signal. And now let's look at what happens when we get to the diode. So remember, diodes allow electricity to flow through in one direction, but they block out or absorb, or they block the electricity from flowing in the opposite direction. So let's look at what happens when we have a positive voltage up on the top of the transformer and a negative voltage at the bottom. So we got a positive voltage there, a negative voltage there. Let's look at what happens. So this anode of the diode would be closer to the positive voltage, so that would be positive. The cathode would be negative. So is this diode forward biased or reverse biased? Forward biased, exactly. So does the electricity flow through it? Yeah. So the electricity flows through. So let's look at the voltage across our load. So the input voltage, so we kind of zoomed in here. Anyway, this is the input voltage. So say this was 10 volts peak, okay? So that means we've got positive 10 volts up here at the top of the transformer and ground down here. So the voltage so the current is flowing through our diode. So what is the voltage across this diode, approximately?
6.7.
Yeah, 0.6, 0.7. We'll call it 0.7 for now. So that's 0.7 volts there. So how much voltage would be across our load? Yeah, 9.3. Exactly. 9.3. So what happens is that on our load, we would see something like this. The voltage would go up to a maximum of 9.3 volts. Okay? So that's what happens when we have a positive voltage there. Now let's see what happens when we have a negative voltage at the top of our transformer. We've got a negative voltage there and a positive voltage down there. Now we have a negative voltage on the anode and a positive voltage on the cathode. So is this diode forward biased or reverse biased? Reverse, exactly. So does the electricity flow through it? No, it blocks the electricity. So now all of the voltage from the supply is across the diode. So how much is left across our load?
All of it.
No, all of the voltage is across our diode. Remember, when it's reverse biased, all of the voltage is there. So how much would be across the load? 0, exactly, 0. So if we looked at our signal across our load here, when the input goes negative, the signal across the load is just 0 volts. Okay? So that would happen when we have a positive voltage down here. And then pretty soon, since this is an AC signal, the voltage would change again. We'd get the positive voltage on the top again. So then our signal would go like that again. And then when the input switches negative again, we get this 0 volt output. Okay? So this is the voltage that we would see across our load. When the input voltage was positive, we'd see a positive voltage there. And when it's negative, we'd see nothing. So this is why this is called a half-wave power supply, because it only captures the positive half of our incoming wave. And it just gets rid of or disregards the negative half. Does that make sense? Okay. So that would be the voltage across our load. Now again, this output signal has these big dips in it and big changes, and that's not great. We're trying to get to a nice flat signal. So what we need is we need to do some filtering. We want to smooth that out. So again, the easiest way to do that, the simplest form, is with a capacitor. So we just put a capacitor here in parallel with our load, and that smooths out the signal quite a bit. So when we have that capacitor in place, now the output it increases and charges up when the input goes up, but then when the input goes down, the capacitor discharges kind of slowly. So it goes down like this until we get to the next point where it would start charging up again. So then it recharges, and then it goes down slowly again until it would get to the next point and recharge, and so on. So when you have a capacitor in place, you end up with a slightly smoothed out wave that looks kind of like that. Okay? And then the last thing is that we would put a voltage regulator there before we actually powered our load, but we're not really going to focus on voltage regulators today. If you are curious about that, we go into that in more depth in ET 322, which is one of the next classes in the series here. So that's really what a half-wave power supply is. We have a transformer. The rectifier is just a diode. We have a capacitor to smooth things out. And then we use that. We could put a voltage regulator in, and then that would power our load. So any questions about the half-wave power supply? OK. Cool. All right. So then let's talk about the next type of power supply, which is a full-wave power supply. So the first part of the full-wave supply takes the high-voltage AC and turns it into low-voltage AC. So what's that again? What component would that be?
Transformer.
A transformer, exactly. So we have transformer here. And for the full-wave supply, we use a center tap transformer. And we'll see why in just a minute. Now, the full-wave supply, so what's the next step after we take the voltage down with the transformer? Almost. We still have an AC signal, a lower voltage AC signal. So what's the next thing that we would want to do? Rectify it, exactly. So the rectifier in a full wave supply is two diodes. So there's one up there, and then another one down here. And with the full wave supply, we have our load over here, and then that goes back to our center tap. And from the bottom, this bottom wire comes up. It does not connect there. It connects up here to the top wire. So this little curved bit means that those two wires that are crossing don't actually connect to each other. It's like jumping over, one wire jumping over the other one. So this is the basic configuration for a full wave supply. So we can look at the signals again. So over here we have high voltage AC signal, and then here we have a lower voltage signal, still AC.
Do we still need a capacitor though?
Yeah, so So let me show you what the signal would look like before we put in the capacitor, and then we can compare it to afterwards. So then over here we have the rectifier. So again, we can examine the incoming signal and look at how that changes after it goes through the rectifier. So again, we could imagine an incoming signal kind of like this that is 10 volts peak. And we can imagine, let's try and look through this circuit and see if we can figure out what the output would look like. So again, we can start by looking at what happens when we have a positive voltage at the top of our transformer and a negative voltage down here. So when we have that situation, we have a positive voltage there, negative voltage there, negative and positive. So let's look at this top diode. Is the top diode forward biased or reverse biased? Forward, exactly. So does the electricity flow through it? Yes, perfect. So the electricity flows through this top diode. So it goes that way. And now it could come down here and it gets to this diode. Is this diode forward biased or reverse biased? Reverse, exactly. So can the electricity flow through here and get back to the transformer? No. So, okay, so it can't go through there. So it has to go someplace else. Well, the only other place it can go is through our load, which is good, because that's what we want. We want to power the load. So then it goes through that load, and then it ends up back here in the middle of our transformer. So how much voltage do we have across this top diode? Approximately? Yeah, about 0.7 volts. Now, we said we had 10 volts peak here, but this electricity isn't flowing to the bottom of the transformer, it's flowing to the middle of the transformer. So how much voltage would we have between the top and the middle there? 5 volts, exactly. We got 5 volts there, and we're losing 0.7 across this diode. So how much voltage do we have left across our load? 4.3, exactly. So we got 4.3 volts there. So our output here, when the input is positive, the output is positive also, but it only goes up to about 4.3 volts. Okay? Any questions about that? All right, so then we can look at what happens in the opposite case when we have a negative voltage at the top and a positive voltage at the bottom. So now this bottom diode has a positive voltage there, negative there. The top one has negative and positive. So is this bottom diode forward biased or reverse biased? Forward, exactly. So the electricity flows through in that direction. What about this top diode? Is that one forward or reversed? Reversed. Okay, so the electricity flows through this bottom diode. It can't go through the top one because the diode is reverse biased. So the electricity has to find a different way. The only other way it can go is through this load. So it goes there, and then again, it comes back to the middle. So again, we have 5 volts on the bottom, and we lose about 0.7 going through the diode. So how much voltage do we end up with across this load? 4.3, exactly. So 4.3 volts there. So in other words, when the incoming voltage goes negative, the output is still positive, but again, it only goes up to about 4.3 volts. Okay. So then we switch back to the original condition, and the voltage goes, the output voltage goes positive again, and then we get back. And so this is what our output would look like. So you can see this is why we call this a full wave power supply. It captures the full incoming wave, both the positive part and the negative part. Unfortunately, the output voltage is considerably lower than the input because we're using this center tap transformer, and so we're only getting about half of the voltage coming out that we would normally get. So any questions about how that works? All right. And then, yeah, again, if we were really building this supply, we would put a capacitor in parallel with our load, and that would help to smooth out the signal a little bit, so you would get kind of a smoother signal that looks something like that. Okay. All right. So then the last type of supply is a full wave bridge supply. So a full wave bridge supply, again, starts with a transformer. In this case, we don't use a center tap transformer. We just use a regular transformer. And then we have a rectifier next. This rectifier is the most complicated of the three. So this one is called a bridge rectifier. So the way I do it is that I draw it like a diamond here, and then there's a diode on each side of the diamond, and they all point to the right, more or less. So they're all kind of pointed in towards the right side. Right? Right? Yeah, things get crazy up in here. All right. So, all right. All right. So that is the rectifier, and then again, that feeds out to our load. So our load would be over here. So that's a full wave bridge supply. So let's talk about how this works. So again, we can assume that the signal coming out from our transformer here is 10 volts peak. So let's see what happens when we have a positive voltage at the top of the transformer and a negative voltage at the bottom. So in that case, the tops of the diodes would have positive voltages on them, and then the bottoms would have negative voltages on them. So electricity would start out up here, it would start flowing. Can it go to the left? Is this diode forward biased or reverse biased? This one is reverse biased. So the electricity, yeah, can't go through to the left. What about to the right? Is this one forward biased or reverse biased? Forward. So the electricity goes through here to the right. And then can it go down through this diode here? No, that one's reverse biased. So the only other path is to go through the load. So it goes down here through the load. And then it comes around here. And now, is this diode down here forward biased or reverse biased? Forward. Perfect. So the electricity goes through this diode. And it flows back around to the negative side of our transformer. Okay? So it went through the load, but in order to get there, it went through one diode and then a second diode. So, and each diode is about 0.7 volts. So together, that means we lose about 1.4 volts. So we started off with 10 volts. We lost 1.4. What does that leave us here? Yeah, about 8.6 volts. So our output voltage goes up to about 8.6 volts there. All right. So then let's look at what happens when we have a positive voltage at the bottom of our transformer. Positive voltage there, negative on top. Again, the sides of the diodes that are closer to the positive voltage will have a positive voltage on them. The other sides will have a negative voltage. So the electricity starts out down here. We go this way. It can't go to the left because that diode is reverse biased. So it all goes through here to the right. It can't go up because that diode is reverse biased. So it goes through our load, comes back around here. It can't go down. Again, that one's reverse biased. So it goes in this direction, and it ends up back here at the top of our transformer. So again, this electricity went through our load, which is good, but it had to go through one diode and then a second diode in its path. So again, we end up with about an 8.6 volt peak coming out there. Okay, so this is what we get. We capture both the positive part of the incoming signal and the negative part. So that's why this is also a full wave power supply. And we call this a bridge power supply because this configuration of 4 components in a diamond shape like that is called a bridge circuit. Yeah?
Sorry, I missed the part. What is the those 2 untouched parts for? Those are for the only when the blue is going on, right?
So which,
So
you mean this one and, yeah, and that one?
Yeah, those are for the non-negative side.
Right. That's, yeah. When the voltage is positive up here, it flows through that diode and that one. And then in the other condition, it flows through the other 2 diodes.
Okay, I just wanted to make sure.
Yeah.
I'm sorry, I'm terribly confused about the portion why the diodes are, I guess, inverted when they're in. Like, for example, the layout has on the bridge has the diodes in positive and negative. So they have, what's it called? Forward bias normally. But the ones behind them are not. They're reverse bias. Is that on purpose?
So you mean like this one is forward biased when we have a positive up there, and this one is reverse biased?
Why is that one in reverse bias when we have a positive on top?
You mean what is making it that way, or why was it designed that way?
I guess.
Well, okay. So let's just look at what causes it to be that way. So when a diode is forward biased when we have a positive voltage on the anode and a negative voltage on the cathode.
Right.
So for this one, we have a positive voltage on the anode. So the part of the component that's closer to the positive voltage gets a positive charge. So in this case, the anode is closer to the positive voltage, and so it gets the positive charge. Over on this one, the cathode is closer to the positive voltage, so it gets the positive charge there, and the negative is on the anode. So that means that this diode is forward biased, and this one is reverse biased.
That clears up a lot. Okay.
Sure. Yeah. Yeah. Other questions?
So no capacitor?
So again, this is kind of what the signal would look like without the capacitor. When we actually build the circuit, we would put in a capacitor to smooth things out. And then when we do that, it does what we've seen before, where we end up with the capacitor charging up and then discharging slowly between the charging cycles. So we end up with a wave that looks kind of like that. Yeah. Yeah.
Would this configuration have about 9.3 volts on the load?
No, 8.6, because the electricity has to pass through two separate diodes each time that it flows around the circuit. Yeah. All right. So these are three different types of power supplies. So you might wonder, well, why did we ever invent three different things that essentially serve the same purpose? Why not just stop when we get to the half-wave supply? You know, we got that, and so why bother with anything else? Well, each one of these circuits has its own advantages and disadvantages. So let's talk about that for a minute. So first of all, the half-wave power supply, one of the advantages of that is that it's really simple. It's just got one component in the rectifier, one diode, so it doesn't get much simpler than that. And simple is often a good thing. It's easy to build, it's easy to repair, and it's cheap because we only need to buy one component, right? So all of those things are advantages. Can anybody think of a disadvantage to the half-wave supply?
A lot of inconsistent power.
Yeah, so there's power for half the time and then no power for the other half the time. So that means, like you said, the voltage can be inconsistent. It can charge up and then go down and up and down. So you get more variation. Also, yeah, you've got a long time for the capacitor voltage to discharge. Even when we're using a capacitor, there's a long time between these humps. So the voltage can discharge more over a longer time. And so, yeah, you get bigger ripples there. And of course, we don't want any ripples. We're trying to get a nice flat signal. So those are a couple of disadvantages of the half-wave supply. So advantages are cheap and easy to build. Disadvantages are kind of a lot of ripple, and also efficiency. It's not capturing half the wave. It's just throwing it away. So it's somewhat inefficient that way. So
Is there also a lot of stress on the capacitor?
I don't think, I mean, as long as you stay within the voltage rating of the capacitor, it should be fine. Yeah. Yeah. So other questions about that? Yeah.
Would it matter the amount of voltage loss? Like that has a
Oh yeah, so that's a good point. Right, so this one, yeah, that's a sort of another positive thing about this one. You start off with a 10 volt signal, you get out like a 9.3 volt signal. So you don't lose much voltage. So yeah, so that's a good point. Another positive thing there. So yeah, yeah.
When I disassemble electronics, I've seen what I think are supposed to be step-down transformers from
Uh-huh.
the main line
Uh-huh.
that are so small that I doubt that they can actually take 120 volts in the first place.
Oh, you can get very small transformers. Yeah, and they can handle
What I
120 volts.
Is if it was common practice to try to attenuate the wall power before feeding it into a transformer, or you just put 120 volts straight into it?
Yeah, typically you just put 120 volts straight in, because if you were to attenuate it, that would be inefficient, and also you would have to do something with that lost voltage. Typically, if you put it through a resistor, that could lower the voltage, but you're turning it into heat. So then you'd have to do something with that heat. Otherwise, you could melt or damage components or things like that. So typically, you would just put the voltage straight into the transformer.
Thank you.
Yeah. Yeah. Really, it's the amount of current that's flowing that will determine the amount of heat that you have. And these applications, if you're dealing with an electronic application, the current is often relatively small. So you don't create a lot of heat in the transformer that way. Yeah. Yeah. So those are some of the advantages and disadvantages of the half-wave supply. For the full-wave supply, can anybody think of some advantages for that? Yeah.
Fills in the gaps.
Yeah, exactly. We don't have those gaps like we did before, so we're capturing the full input wave, so that's good.
So this is a lot of voltage though.
Yeah, exactly. So that's one of the drawbacks. So, right, we start with 10 volts, but we end up with 4.3. So that's a negative there. Yeah.
Depending on the desired output voltage, could the high voltage loss be a good thing almost?
I mean, I suppose you could design the transformer to be so that it puts out whatever voltage you're looking for. But yeah. So you could design it to put out what you want. So yeah.
But wouldn't a benefit just be initially converting it to a lower voltage just so you didn't lose the extra voltage? Because isn't like something amount of volts like a certain amount of money? So you'd still be losing money when it.
Well, the power company actually charges you for kilowatt hours. So, and a watt is a unit of power, which is volts times current. So yeah, they're really charging you for power. So if you have a low voltage and high current, or a high voltage and low current, they could work out the same. Yeah. So those are a couple things. One other thing I wanted to point out about this is that we're using that center tap transformer. So that's actually one of the drawbacks to this type of supply, because it turns out that it's a little bit more difficult to manufacture center tap transformers. You have to go, you make the regular transformer, and then you have to go back in and find the center and then attach a wire there. It just takes a little bit longer, and so it is a little bit more costly to manufacture those types of transformers. So that's one drawback there. So, yep. So that's the full wave supply. And then the full wave bridge supply, it's kind of the best of both worlds. Well, no, it's more complicated, but it's more efficient. So, so it has the full wave output. It's got a higher voltage, but of course it's got more diodes, so it's a little bit more complicated there. Fortunately, it does not have that center tap anymore, so we don't have to spend the extra money on that.
You do on the diodes.
Right, you do on the diodes, but it turns out that this supply, this type of supply and this type of rectifier is so common that some circuit manufacturers, some chip manufacturers actually make a chip now that has these 4 diodes built in one chip in this configuration. So rather than buying 4 separate diodes, you can just buy that chip because it's so commonly used that way.
So would you say the full wave bridge is the most like overall efficient and the most cost effective?
So it is the most efficient, and it gives you the nicest output. It gives you the highest voltage and the smoothest output. It's a little bit more expensive than the half wave supply.
But is it cheaper than the full wave?
Yes. Yeah. So typically what happens is that if you're going to build, you will either use a half wave supply or a full wave bridge. Not many people use a full wave supply because of that center tap. So if you are building something cheap and you don't really need a nice smooth power supply or a lot of efficiency, then you can get away with a half wave supply, and people do that. If you're building something that needs a little bit more precision, a little bit more efficiency, people typically use a full wave bridge supply. Yeah.
So most PC power supplies are they full wave bridge?
Yeah.
Okay.
Yeah. Mm-hmm. Yeah.
So you were saying that not a lot of, or the full wave supplies don't get used very much.
Right.
Did they come first and then full wave bridge kind of came after and people started using those more, or?
Probably. You know what? I'm not 100% sure on the history, but probably, yeah.
Okay, cool.
Yeah. Yeah, so those are 3 specific examples of power supplies. So any questions about those? All right, then let's go on and do the preview of today's lab. Okay, so the first part of the lab here says that we're going to open multisim, and we're going to look at a signal. We're going to record the AC voltage. And the first circuit is going to be, we're going to record what these are. And then we're going to next open a half-wave rectifier circuit. Okay? So, so let's look at the half-wave rectifier circuit here. Oh, what happened there? Anyway, so this is the half-wave rectifier circuit. So what is that noise in the vents? Huh?
It's been making that noise all semester.
Oh, okay. Okay. All right. All right. So this is the half-wave rectifier power supply. So you can see we got a power supply, or a AC voltage coming in, and then a transformer, and then our diode, which is the rectifier here, and then that's going to our load resistor over here on the right. So this thing up here is a virtual oscilloscope. And you can see that one channel of the oscilloscope is hooked up to the input and the other channel is hooked up to the output. So we're going to run this circuit and we're going to see what these 2 signals look like. Now, I'm not sure if you can tell on the screen up there, but this wire on the left is a red wire and the wire on the right is a blue wire. So when we look at the oscilloscope, whatever wire is red is going to show up as a red trace on the oscilloscope, and whatever wire is blue is going to show up as a blue trace. So we could actually change those around if we wanted. We can double click on that and we could change the color if we wanted to. But we're going to leave that blue and red for now. So we're going to run this circuit, and then we can open the oscilloscope, and we see the signal bouncing around there. So it's probably really hard to see the signal on that black background right now. So what I'm going to do is I'm going to push this reverse button, and that makes the signal show up a little bit more clearly. So I'm also going to use a trigger. Right now, the signal is bouncing around on the screen, kind of like we've seen the signal bounce around on our oscilloscope screen. We remember that it does that when it's not triggering properly. So I'm going to set the voltage level. Well, first of all, I'm going to set the trigger level to be single. So that just means that it takes a picture of this signal and captures it on the screen. All right, so we got this signal there now. Right now we can see the blue signal, which is the output, but we can't see the red signal, which is the input. And there's a reason for that. So the red signal is channel A here. And if we look at channel A on the oscilloscope, we can see that right now the input is at 0. So this just means that it's always going to display as 0 no matter what the input signal is. So I'm going to switch this over and make this a DC input. So now when I do that, we can actually see the red signal and the blue signal. So, and we can even make this bigger if we want so we can see it more clearly. So this should look kind of like what we drew on the board. We can see the red signal is the input. It's going up and positive and negative. And then since this is a half wave supply, we can see that the blue signal goes positive, but then when the input goes negative, the blue signal is just, it stays at 0. Okay? And then when the input goes positive again, the blue signal goes up. And again, the blue signal doesn't go all the way up as high as the red input signal. And why is that again? Right, exactly. Because of the diode. The blue signal has to travel through that diode, and we lose a little voltage there. Okay? So that's what's going on there. We can also change the time scale. In other words, we can zoom in the horizontal direction, because we're going to have to draw this in the lab book, and we maybe don't want to draw 10 waves there. So if we want to change the time, or zoom in the horizontal direction, we can change this around. So we want to have at least 2 full signals on the screen, 2 full periods of the signal on the screen. So we could make it something like that. And then when we're happy with that, we can stop our simulation and then go back to the lab book. And then you would draw this signal in your lab book, and you would do it the way that we've drawn other signals. So you would show the volts per division, you'd show the seconds per division, and you would show the peak value and the amount of time for one period as well. So you would sketch that in your lab book. So any questions about that? All right. And then you do a similar thing for the full wave rectifier circuit. So we come over here, we would open the full wave rectifier circuit. Again, we run the simulation, we can open up the oscilloscope, and then we'd make these adjustments in order to see a nice signal. So again, the adjustments that I make, personally, I reverse the color so that it's easier to see. I can make the window bigger so that it's easier to see. I turn on the triggering. I make it single triggering. And then I can adjust the time scale in order to zoom in a little bit in the horizontal direction. Again, keeping at least 2 complete cycles of the incoming wave there. So that's, and then when I'm happy with that, I can pause that and then draw that in the lab book. So questions about that? All right. So that's that one. And then the next part is filtered half-wave circuits. So again, the easiest filter, the simplest filter, is just a capacitor. So you're going to use a circuit and you're going to simulate what the output would look like with a 100 microfarad capacitor and then with a 1000 microfarad capacitor. Okay? And you're going to see how the output changes. So one of these capacitors will probably be better at smoothing out the signal than the other one. So when we put one of them in, the signal should look better, but a little bit wavy. And then if you change the capacitor, the signal should get even more smooth. So you can experiment with that and figure out which one will give you better smoothing. And you're gonna draw the results on this graph there. And then there will be a virtual DMM there, and you can measure the DC voltage on that virtual DMM. Okay. You're going to do the same sort of thing for the full wave circuit and draw your results down there. And then you're going to build a real half-wave rectifier circuit. So for this, you're actually going to build a circuit on a breadboard. So we're going to use these transformers, the same type of transformer that we used earlier in the semester. This is the type that actually plugs into the wall, and you've got 3 outputs there. So you can use these outputs, and then you're going to construct the circuit as it's shown here on the breadboard. So this 1N4001, that's a diode. That's the name for a type of diode. So you're going to put a diode in there. You're going to put this load resistor here to simulate whatever work you're trying to do. And then you're going to measure the output at 2 points with an oscilloscope. So you're going to hook one oscilloscope cable right here to this point. So that would be the signal that's coming from the transformer. And then you're going to hook another oscilloscope cable to this point right there and measure the signal there. That would be across the load. Okay? And then you're going to draw what that looks like on this graph. Bless you. So that would be, is there any filtering in this circuit up there? No, there's no filter in that circuit. So in this graph, you're probably going to see, an output that has those big valleys in it because there's no capacitor to smooth it out. But then down here, we're actually going to add a capacitor. So this is a reminder that electrolytic capacitors are polarized, so you have to pay attention. This is a circuit where your capacitor will blow up if you plug it in backwards. Okay? We're using higher voltages and higher currents here, so this capacitor will explode if you plug it in backwards. So this is a chance, a time when you really have to be extra careful when you're plugging these in. Okay? So please pay attention to the direction where you're plugging in your capacitor. So this shows you, this reminds you which side is positive and negative on a capacitor. And so then over here, you're going to add the 10 microfarad capacitor in parallel with the 1 kilo ohm resistor. Now, up here, the place that you would put the capacitor is in parallel with this load. So in other words, next to this resistor. And the negative side of the capacitor is going to go into ground down here. Okay? So that's how you know which way to plug in the capacitor. The negative side goes to ground. And then the positive side would go to the top of the resistor. Okay? So you're going to do that with the 10 microfarad capacitor. You're going to sketch your output here. And then you're going to repeat that with a 100 microfarad capacitor. So the only thing you change in that circuit is you pull out the first capacitor, you plug in the second one, and then you sketch the new signal down there. And then there's just a couple questions at the end of that lab. So any questions about that? All right, then I'll take attendance and let you go.